Similar to before, we're going to start with a fairly basic, naive version of our data structure before eventually evolving into the great Kwisatz Haderach of array-based lists. So what we're going to do is start by observing a fact, or actually I'm just going to give you this fact, which is that if you're given an array in Java, you can retrieve any item in the array very quickly. So you have 1,000,000 items, and I want this one. Okay? It turns out that if I ask for item 500,000, the computer can do that quickly. And that's just how computers are built, and it doesn't matter how big the array is. Now, why is that? Well, that's going to be a 61C question, and a rough picture of it is because every single box is the same size, the hardware is able to easily and quickly find the item that is needed. Okay, so there's a bunch of wires, basically, is the answer. And those wires go to every single bit of memory, and you know exactly where everything is. Okay, but that's 61C. And yeah, doesn't matter how big it is, though I have an asterisk here because if it's too big to fit in memory, then you might need to start using a hard drive or whatever, but that's not really important right now. Okay. As far as we're concerned, in 61B, getting something from an array, no matter where it is very fast. Okay? So given that fact, our goal is to figure out how do we build an array version of this. Okay? And in lecture, we're only going to talk about the back operations. We're only going to stick stuff at the end of our lists. In Project 1A, you'll be doing the front operations. Okay? So let's try it out. Let's try and build such a thing. Let me open up here. Here we go. Okay. So we have here our starter code. It's all blank. And as I mentioned in the announcements, there is now the folder is now called DIY if you want to do this yourself. Okay? So this is the AList, and well, let's start building some stuff. So it's going to be array-based. And for now, we're just going to have integers. And I'm going to say, okay, well, obviously then the thing we're going to store stuff in, this time instead of a bunch of nodes that are linked together, we're going to have some set of items. So I'll call this all the items, okay? The stored integers. Okay. And likewise, as before, I'm going to have a size, I'm going to have a size here. And I'm going to initialize those in my constructor. So suppose someone comes along and says, I want an AList. Okay? Well, then I'll say, okay, well, the size is 0. There's nothing in there. And items, well, I'll instantiate an array. Let's say of size 8. I don't know, arbitrarily. Okay. Actually, I'm going to go with 100 because it matches the slides later better. All right, so 8, 100, whatever you want. So I have an array of some size. And then when I want to insert, well, then I merely need to set the appropriate thing to x. That is what insertion is. And of course, I also need to increment size. Okay. Where do I put it? Okay, well, at this point, it seems natural since I have nothing. Let's say I have nothing, that I'll put it in position 0. Okay. But that doesn't work, of course, because that will only work as long as there's nothing in the front. So what I'm going to do is I'm going to conceptualize my array list as here's the 0, or like this is the front, after, front, after, front, and so forth, all the way to the back. Okay, that's going to be the scheme. Right? So if I start with an empty array list, that's all just a bunch of nothings. Then if I insert, say, 5, it goes there. If I insert 9, it'll go there, and so forth. And if I insert another thing, it'll be 13. That's going to be the scheme I'm going to go with right now. You could go the other way if you wanted, but I find that this way is easiest. Okay? And one thing that's really nice about this structure is that the position, all right, so I'm going to make an observation, using this particular idea that the next item goes here. Say we have this array right now, and we want to insert. This is the 0th position, 1st, 2nd, and 3rd, right? And right now, size is 2. Or sorry, 3. Right now, the size is 3, right? There's 3 things in there. The neat thing is that the next item always goes in the size position, all right? So that's going to be my convention. And again, there are other conventions, but that's the one I'm going to go with. So I'm always going to say it goes in position size, okay? And that's nice because as soon as I increment the size, I know the next thing is going to go in that position. So if the very first thing we ever insert goes in position 0, the next one will go in position 1, the next one in position 2, and so forth. Okay, so there's a little bit of subtlety there, but I hope that made sense. Okay, how about getting the back item? Okay, so the next item to be inserted will always go in the size position. So you might think to yourself, this is a good time to pause and figure out, okay, well, I'm supposed to return items something. Okay, all right. I'm going to spoil it in a second, but you really should come up with a guess before proceeding. Okay. So if size is always the blank spot where the new item is going to go, then the target item will always be in position size -1. So I guess last actual item index, I guess you could say a size -1, and then I could do last actual item index. It's a little verbose, but yeah, if you wanted everything spelled out for you in text, that would work. Though I think it's perfectly fine style code-wise to just write that. Okay, but I'll leave it this way for now. Okay, I want to get the ith item in the list. Well, I've decided that I'm always just going to leave the front item in position 0. So in this case, it's actually going to be fairly simple. It's just going to be return items I. And how about size? That will be size. And how about delete? Well, I don't want to go there yet. I want to move it down here. I'm going to do that one last. Okay. So that's a basic array list. Okay. You may, if you're paying close attention, already see where we're going to run into some problems, but we'll get there. So this is a basic array list. Let's make sure it compiles. Okay, it did. Marvelous. Okay, yeah, cool. Okay, so let's look at our code. Oops. So here's our A list, right? This is the code we just wrote, compacted a little bit, and slightly different than the version we just typed out. But that's basically the code we just wrote. So I want to raise a point here, which is that we have a number of invariants, okay? In particular, the position of the next thing that we want to insert is always going to be size. Size, you can think of, could also be a synonym for that is next item. Okay. Size, of course, is always the number of items in the A list. And then the last item in the list, the last thing that's actually there is always size -1. Okay. So given these invariants, right? And by the way, invariants, in case you don't remember from last lecture, those are things that must be true about our list. Those are nice features. If we keep these in mind, they give us 1, something to hang our reasoning on, right? Thinking about code is hard, but if we know these to be the invariants and we have them listed somewhere, maybe on a post-it note on our screen, then when we're writing get methods, we just have to refer to this information. And we're writing insert methods, we just need to make sure we can take advantage of them, and we need to make sure that we preserve them, that they're never, ever ruined. Okay? Before we implement delete, let's talk about what it actually means to delete, and we'll use our invariants as a guide. So, a question for you. If we wanted to delete back, what do we actually need to change, right? So delete, obviously everything in Java is just bits, so we have to change some bits. So the question is, which of these memory boxes do you need to change? So we have size, which is a 32-bit box. We have items, which is a 64-bit address box that points at this thing. We have all of these int boxes, all 100 of them. Which ones do we need to change, okay? How many? And what should we change them to? And if you need some tips, look at these invariants and think about what the invariants are. So if these are the invariants, what should delete be? Okay. So I'll just say in terms of the invariants, right? The only thing we need to do to make sure delete works is we need to make sure that all of these things are true. Okay. So in particular, we obviously need to decrease size by 1. And the other thing we need to do is make sure that the last item in the list, that get back will work right. So in fact, actually just decreasing size by 1 is all we need to do to delete. So we just change this to 5, the number is deleted, right? So let's try that out in code. All right, so if we wanted to delete something, first, well, one of the things about deleting is we need to return the deleted item. So we'll need to do the following. We'll need to say int item to return. And I'm lazy, so I'm just going to say get back. Okay, we already have a get back function that will get the last thing. And then we could say size equals size -1. Okay, and then we can return item to return. So this is the process of deleting. Now some of you may have thought, okay, well don't I also need to zero out this? Don't I need to set this thing to 0? And the answer is that strictly speaking, no, you don't really need to. But it doesn't hurt to do that. Okay, so I'm also going to say items size -1 equals 0. Okay, so that's just going to be me zeroing out the last item. And again, right, not strictly necessary, but it's a good habit. We'll see why soon. So if we look at our code, these were our basic operations. This was our delete back operation. written a little different. So here I was not as lazy. In this case, I actually rewrote getBack. I actually prefer using getBack a little more, but just to show you, you could rewrite it and that would be fine. So setting this item to 0, as I mentioned, is not strictly necessary, but because if you think about it in terms of our invariance, I think this is a really interesting point. You should convince yourself. You should understand. And if you don't understand, you should ask at office hours or discuss with your friends why you don't actually need to do this. Okay? All right, so that's delete. So let's reflect on what we've achieved with our AList and see its limitations. So there should be a big elephant in the room for you here. So in the case of this array list that we're building, inserting, getting, deleting, so forth, they're pretty sensible operations. We just need to use some subset of the entries of an array. So if we only have 6 items, we're only using the first 6. And that's our naive array list. Okay. So what's naive about it? Let's discuss that. You probably already sensed it. It has a lot to do with this. Okay, so the core idea of our array list is we have some array, and we only use part of that array. And all of these methods are just convenience methods to make sure that the right part of the array is being used in a given time, right? And of course, the natural problem is, let's suppose now we have 100 items, right? We've filled in all of these data. Everything is marked as actually used. The size is 100. This stuff is all good. The question is, what happens if we insert into it? Okay. Well, what'll happen is, of course, we'll try and insert into position 100, and it's just going to freak out at us and get mad and say there is no such position. So what should we do about it? So you might consider that for a moment. And the idea seems kludgy, but is really how it works. So let's check it out.